Hello, and I would like to welcome you to my PhD defense talk titled Objective Quality Assessment of Perceptually Coded Audio Signals. I would especially like to greet and thank the members of the evaluating committee, Professor Andre Kaup, Professor Jürgen Herre, Professor Thomas Sporer, and Professor Mark Stamminger. I will hopefully give you an engaging and concise account of the research that I carried out, and I eagerly wait for some questions from the audience after I am done. So I would first like to talk about the motivation for this research on the impact of perceptual audio coding. So in the beginning of the early 90s, perceptual audio codecs actually caused a revolution in the multimedia industry because by exploiting properties of human auditory perception, perceptual audio codecs can actually increase the audio transmission and storage efficiency by 10 times or more without the loss of perceived quality. So even today, codec development is actually a very active branch of research because we need larger volumes of high quality communication data and media content streaming, for example. So the race for more efficiency in coding and best quality in perceptual audio coding actually continues as of today. So therefore, it is crucial that we have a fast development time to market for these audio codecs as the technology progresses at a very fast pace. So I'll give now an overview of the talk. We just gave the motivation. Now a little bit of the introduction for the basic concepts. For example, what does it mean to perform subjective quality assessment in codec development? Then the use of algorithms for audio quality assessment, usually called objective quality assessment, then some of the limitations for these algorithms, and then we'll jump right into the first and second contributions of this thesis related to measurement of timbre aspects and spatial aspects of audio quality. Then we'll be presenting some results of these contributions, or the addition of these contributions, and some summary and conclusions as well. So let's start out by defining what does this subjective audio quality assessment means in terms of codec development. So let's say we have, for example, some requirements for the development of an algorithm, for example, a given data rate or a use case, such as a voice codec or a music codec. And then we do a first test and we give this algorithm to listen to, or the signals processed by this algorithm to listen to different subjects, and we gather opinion, preferences, and quality scores mostly. And we perform some subjective assessment. After some statistical analysis of the quality scores, then we get some feedback to the developers, and then we do it again with some adjusted changes and parameters and some new alternatives and so on. The problem with this development cycle is that it takes a lot of time and resources. For example, we need to gather many listening test subjects. We need to train the subjects as well. We have to use expensive listening tests with low distortion to be able to really hear what's going on with the signals. We need to design good tests for statistical usefulness of these results as well. But we can actually be faster if we use algorithms to predict subjective quality scores. So we need to mimic the subjective assessment process. For example, when we present a reference and a degraded signal to a subject, and then it emits its opinions in the form of a quality score, we can do the same with an algorithm by presenting the audio material to the algorithm, and then the algorithm would emit its opinion score or the prediction of what a subject would say. This concept of artificial listener has already been presented more than 40 years ago by Schröder in 1979 and Brandenburg as well. They were the first to try to model subjective assessment using human perception on some quality metrics. The thing is, if we want to use these objective assessment algorithms, we need to calibrate them and validate them by comparing them to some listening tests to be sure that we are doing the right thing. For that, we have different performance metrics of comparison. What we'll be using in this presentation is actually the subjective objective score correlation. That means there's a measure of similarity of the outputs of the model and the outputs of the listening test subjects. But there are other as well that we can use. For example, accuracy, which is the error between the two, and so on. So we will be focusing on objective subjective score correlation for these reports. So I will now talk about a little bit about the current state and the limitations of the algorithms. Over the years, the best approach has been shown to be to mimic the auditory system in these algorithms, and therefore we call this perceptual objective quality assessment. There are already many algorithms that have been standardized through the years to facilitate the measurement of the quality. For example, the perceptual evaluation of audio quality, which is an ITUR recommendation. There is also the perceptual evaluation of speech quality, the perceptual objective listener for quality assessment as well. All these current algorithms have more or less the same problem, and it is that they fail to predict subject responses on different cases consistently. For example, they may be tuned to a specific signal type or application, voice or music, or some coding technology. For example, there have been reports on limitations for codecs that use parametric representations of the waveforms, for example, bandwidth extensions, or codecs that cause spatial distortions, so split stereo distortions. So in order to talk about the first of the contributions, I will first introduce you to the general structure of a perceptually quality measurement system. As I said before, we mimic the listening test process in which we present the reference and the degraded signal most of the times. And then we do some pre-processing, for example, some level adjustment or some time alignment. And then we start by modeling human auditory perception. The first step of modeling this human auditory perception is actually starting out with the peripheral effects. Peripheral effects is referred to everything that happens in the process of converting the sound signal into neural responses that go straight to the brain. These perceptual representations have, for example, they take into consideration effects such as loudness or auditory masking, and they have been extensively researched here. We can go further, and then we can compare these perceptual representations and do some feature extraction, and then produce different distortion metrics that correlate with the human perception of degradation in different dimensions. For example, we have measurements of noisiness, we have measurements of roughness of a signal or dullness, and we can go further then and combine all of these metrics into an overall quality score that will emit the objective opinion of the quality of the signal. As I said before, this first part of the peripheral effect has been extensively researched in quality measurement and also in perceptual audio coding, and my contribution will mostly focus on trying to extend this part, which is related to cognitive effects, and this is mostly what's happening around the brain or the first parts of the brain, and it's related to how do we make sense of the sound that we hear. So we will go now to the first contribution of this thesis. It is related to this Timbre quality measurement or the Timbre aspects of quality degradation. Let's say, for example, we have different metrics here, and this is what it has been previously done in order to combine these metrics. Let's say we have these different metrics, and we have a dullness metric. A dullness metric will work best when the signal degraded sounds like this. On the other hand, if we have a roughness metric, it will describe quality degradation when it sounds probably like this. And then if we have a noisy signal, then we may use the noisiness distortion metric. So the question that we need to ask is the signal degraded because it is dull, it is because it is rough, or maybe a combination of both? This is a very subjective question, and for that we need subjective data to train this combination model and to combine all the metrics into an overall quality score. So the previous approach was actually to use general purpose machine learning methods for this. The problem with this is that they were not really good at predicting unseen data beyond the training data as well. So as the technology progresses, this data might be outdated as well. So they usually show poor prediction. So the first part of my contribution was to find out what can we do to improve this prediction. And of course, since this is considered a very basic cognitive model, I said, okay, let's add some more cognitive effects to this model. So the first contribution tried to extend the cognitive model by using metrics related to sound structure and pattern analysis in the brain, which are also kind of cognitive effects that can be derived from this feature extraction stage. So if we have a degraded signal that sounds like this,
The red flashing button, press it. Ah!
and in another case a degraded signal that sounds like this,
The red flashing button, press it. Ah!
we can see that in both cases the degradation are audible and more or less equally loud. A peripheral model that only considers disturbance audibility, that is to say disturbances above the masking threshold, and disturbance loudness would grade these degradations as equally severe. However, the second degradation sounds clearly more severe than the first one. A reason for this is that the structure of the second disturbance does not resemble the input signal. The structure of the error signal is not similar to the original signal, whereas in the first one, the disturbance integrates into a single percept with the signal due to the fact that they have similar structures. So a cognitive effect metric could actually measure structure similarity, for example, to inform a combination state. So we may do this. We may implement some cognitive effect metrics that are related to structure and pattern analysis. This has been done, for example, already by Behrens in '96, but Behrens only related this cognitive effect metrics to only one single distortion metrics and not a combination of the distortion metrics. And this is therefore my question, okay, how do cognitive effects interact with multiple distortion metrics to form a single quality score? So we found out that actually there are interactions between cognitive effects and distortion metrics. Here we have the analysis of a listening test database and the outputs of the model with different cognitive effects and different distortion metrics as well. Here's one example that analyzes the probability of a signal being speech-like and the usefulness of a dullness metric. Let's start by taking a look at this graph, and we see here a list of different signals coded with many different coding technologies. Yeah, and the first line that goes across all these items is actually the probability of a signal being speech-like, which is a cognitive effect. As you can see, for example, for signals that have been labeled as speech, we have here a very high probability that they are speech-like here as well. And then for signals that are mostly music or mixed signals, we have the probability of speech-like quite low as well. On the other hand, we have here in the blue line the usefulness of the dullness metric. That means how useful it is, this dullness metrics, to measure quality degradation. How much of an impact does this metric have in overall quality degradation? And we see that coincidentally, where the speech signals are actually quite high in probability, the usefulness of the dullness metric goes down, and for signals in which the speech probability is low, it's actually very good for measuring quality. So the first conclusion was, okay, so the speech probability of a signal predicts the salience or the usefulness of a dullness metric. We can go a little bit further than that and actually implement some kind of threshold in on the cognitive effect and say, okay, only use dullness when the probability of speech is below a threshold, and this is the orange line represents actually the thresholded red line as well. With all this information for many different cognitive effects and many different distortion metrics, we have found interactions that we can put into an interaction model. And this is actually the core of the first contribution, is the replacement of the combination stage with an interaction model that is perceptually motivated. Yeah. So here we have the influence of different cognitive effects in yellow, and then the different distortion metrics, and they are combined in the following manner. First, we have some salience weights that dynamically weight the distortion metrics with the cognitive effects for the selected interactions with the previous analysis. Then we have this thresholding effect that I talked to you about before, with models the cognitive effect detection and saturation of the thresholds using the sigmoids. And then we have some basis functions that basically translate the roughness or the dullness or the noisiness metric values into a readable quality scale. For example, 0 being really bad and 100 being really good. So with all these three components, we can actually put it into a quality measurement system. We can replace the combination stage with this proposed interaction model, and we have two variants, one using this sigmoid threshold and the other one without using it. So we see that we already have a difference in performance. As I said before, we will be measuring the performance in terms of similarity to subjective scores. And we also see that the proposed combination model actually really outperformed the other variants that used established machine learning quality mapping for the combination of the metrics. And also we compared some other established objective quality metrics or objective assessment systems for a variety of speech, music, and mixed content signals and different reverb conditions, etc. We have also bandwidth extension, we have parametric codecs as well, and so on, for quite a lot of listening test scores. Yeah. So in summary, the contribution is that there is a novel concept for incorporating cognitive effects to quality measurement. This architecture for incorporation of the cognitive effects is actually perceptually motivated as opposed to general purpose machine learning. And there is an explicit model of interaction with the distortion metrics, and we don't let the machine learning algorithm do that. And therefore it outperformed, or we found out that it outperformed general purpose machine learning algorithms by a large margin, and it outperformed also other state-of-the-art systems. So we will now pass on to the contributions for spatial audio quality measurement. This is the second contribution. And for that, we need to talk a little bit about the fundamentals of spatial audio perception and the sound localization of auditory sources. When we have two or more loudspeakers, we can create intensity or channel level and time differences to cause the impression of localized sound sources in space. If we take a look at what's happening in the incoming ear signals, we see that we have interaural level differences and interaural time differences that can actually happen between the left and the right ear. We can compare them and actually estimate the location of an incoming auditory object. Yeah. Also, we can compare the signal similarity between the left and the right ear, and this will give us an estimate of the spaciousness, impression of spaciousness of an auditory object. Yeah. With these three binaural cues, we can describe an auditory scene in space quite well. So the first approaches, or the previous approaches for measuring the distortion of spatial audio quality, was actually to use these binaural cues in a direct comparison and just emit distortion metrics based on these binaural cues. For example, this is an extension of the perceptual evaluation of audio quality recommendation for measuring spatial audio quality. What it has been done before, we have some stereo multi-channel signals and we convert them into ear signals using some head and room filtering. This head and room filtering actually mixes down the multiple signals into two ear signals, considering the properties of the head and the properties of the outer ear, and probably some room reflections for the listening room in which the signals are listened to. Once we have this transformation from the multi-channel signals into the left and the right signals, we process these signals with a binaural model that basically extract these binaural cues that I talked to you about, and also some perceptual representations and before. And then in the end, we have some lateralization distortion metrics related to the perception of arrival of an auditory object in the horizontal plane, and also some envelopment distortions related to the interaural cross correlation. We add them to the existing Timbre metrics, and then we have a quality score with new data. The problem is that some of the cue distortions are actually more important than others, and within multiple auditory objects in a scene. So for that, we actually need a more, let's say, complete representation. Yeah. And for that, we come to the second contribution, which is to use a binaural loudness model for extending the representation, the perceptual representations of the signal to a spatial case. Yeah. And for that, we take the reference and the degraded ear signals, the two signals, and we do a directional estimation based on the spatial cues, but we also do some kind of mix down. So we mix down these two signals into one, and then we calculate the loudness of the different objects. And this is performed into a time frame and perceptual spectral band wise condensing. And for that, then we come to this pooling part, which is basically we do a kind of histogram in which we pull loudness values according to direction of arrival values. And then in the end, we process these histograms through a spatial spreading or masking model, which condenses all the spatial masking properties. For example, if we have two objects that come more or less from the same direction, the louder object will probably mask some properties, auditory properties of the quieter object, yeah? And if the objects are actually coming from different directions, this masking effect may be lower, yeah? So after all that, we produce what we called here the directional loudness map for reference and degraded signal, and we can see right away that for the reference signal there are some differences, and we can here is, for example, a wider spread of the loudness than here, and this can give us already the impression that we have distortions in the sensation of the envelopment. We can introduce this into a system very similar to the one before, but this time comparing the spatial representations and then producing, for example, some loudness metrics based on spatial disturbance, which is actually an extension of the noisiness metric happening in peak. And then we can compare the performance of this model against the state of the art. We did that with many spatial audio in many different channel formats and stereo formats as well. And we came to the conclusion that the Timbre baseline was actually not that good, but already if we implemented binaural models, the performance increased, and our model was actually most of the times better than the state of the art as well. So we now come for the final part of this presentation, which is actually the combined performance of the two of the contributions, and also the performance compared to the state of the art. Yeah, and for that we have this overall performance metric in terms of subject response prediction or correlation of the objective outputs to the subjective scores for a variety of different listen and test databases that include different coding technologies, different channel configuration, different signal types, and close to 1,400 mean scores condensed from thousands and thousands of listeners in different listening test labs. Yeah, and here we have our contributions, namely the contribution 1 and 2 summed together, and the contribution 1 only, and then the rest of the state-of-the-art systems. Most of them are standardized, but there are other that are quite new as well. And we can see right away that for our contributions are the only ones that reach a consistent and strong prediction across all the different cases, whereas in the state-of-the-art, many of them have failed to predict in some of the databases as well. So this is the first result that I wanted to show you here, that these contributions actually allow us to have a consistent, strong prediction across many different cases. Now we'll analyze shortly the effect of adding spatial distortion measurements. So that means adding the spatial distortion contribution C2 against only using the contribution 1. And we see we have two cases. The first one is that when the use of spatial metrics actually decrease performance, and when the use of spatial metrics actually increase performance. Yeah. And for that, we have to shortly take a look at the composition of the two databases. These are both stereo. These are both the same listening test type. But in the decreasing databases, we have a fairly good quality. And in the other quality, where actually using spatial effects was we gain some performance by using a spatial effect. This is actually fair quality. It's lower quality. If we take a look at the codecs that have been used and also the bit rates, we can see that for this database in which we benefited from using spatial audio quality, we were using spatial parametric stereo tools, which is to assume that the spatial distortions play an important role in overall quality degradation, whereas here, which we have separate channel audio coding, I assume that this is mostly the degradation comes from timbre degradations and not with spatial distortions. So to say, okay, if we want to use additional spatial distortion features, we need to make sure that the spatial distortions play a significant role in quality degradation. Yeah. So as for the observations, again, the two contributions shown in this thesis actually provided a more robust quality measurement across many different cases. Again, in cases where the signal was actually speech, where the signal was actually music, or with different reverb conditions, with different channel configurations, and actually with different coding technologies, parametric, stereo, or spatial bandwidth extension algorithms as well. Only the problem is that if we want to measure spatial quality, we have to make sure that the presence of spatial distortions in the data is actually prominent, and it leads to a quality degradation, because otherwise we would be adding extra features to the distortion to quality estimation stage, and this will cause, of course, noise in the system. So it is very important. For example, I've noticed the tendency that for high quality coding, there's actually no improvement against the Timbre baseline, because there are in fact not so many spatial distortions. But for fake quality coding, that means audio codecs in which we have parametric stereo tools, for example, there is an improvement in spatial quality. Nevertheless, we need to focus on future research that allows us to predict when this quality degradation is happening because of stereo signals and when it is not, yeah, and when to use these spatial distortion metrics. So as for the summary and conclusions now, we've seen that quality measurement systems can actually save time and resources, provided that they accurately predict subject responses. Otherwise, the evaluated state-of-the-art systems actually failed to predict subjective responses consistently across different degradations. So this work actually proposed two concepts to extend perceptual models used in audio quality measurement. The first one is actually that there is a novel way of modeling cognitive effects and their influence in distortion salience, and the incorporation also of directional loudness and spatial masking of disturbances for a more complete representation of the spatial signal within the quality measurement system. Yeah. So as I said before, the proposed system with the two contributions actually outperformed the state-of-the-art quality measurement system analyzed, and it showed a consistent subjective quality prediction across a variety of degradation and technologies, also due to parametric coding, to stereo and spatial audio as well. And we need to actually further evaluate these ideas in different systems for different applications. Let's say, for example, signals degraded due to blind source separation algorithms as well. So this marks the end of my talk. I hope you enjoyed it, and now I am open for questions. Thank you.